So what we've been doing for the last couple of classes is looking at recursion, which is one of the key topics on the course. So we kicked things off by doing lecture 6, which introduced the idea of recursion, or defining things in terms of themselves. And then what we did last time around is we moved to the iPad and we did some exercises on recursion. So what we're going to do today is move things on a bit. We're going to be looking at chapter 7 from the book, which is about higher order functions. And actually this is going to be the last of what I would regard as being the core topics for the course. So we will be doing more stuff for the rest of the course. We're only about halfway through, but this is the point where when we finished higher order functions, I think we finished the main things which I want to teach you about simple Haskell programming. And then in the rest of the course, we're going to look at a few more sophisticated features, and we'll be doing a few more worked examples and exercises and so on. So we'll kick things off today with a definition, as we often do. So the subject of the lecture today is higher order functions. So you can ask yourself, what actually is this? Well, here's a simple one-line definition. So we're going to call a function higher order if it either takes a function as an argument or it returns a function as a result. So if you're studying this course in Nottingham and I asked you in the exam, maybe for 1 mark, what's a higher order function? This is all you need to write down. It takes a function as an argument or returns a function as a result. So as usual, let's have a simple example to illustrate what's going on. So what I've defined in the slide here on in the blue box is a function called twice. So if we look at the equation first of all, we can see that twice is a function which is taking 2 parameters. It's taking a parameter called f as its first input, then it's taking a value called x, and all it's simply going to do is apply the function twice to the argument. So we apply the function once inside the bracket, so fx will return a result, and then we take that result and we apply the function f to it. So we can see here that twice is a higher order function because its first argument, f, is a function, which we're here applying twice. And this point is further emphasized when we look at the type. If we look at the type for twice, we see that it takes 2 parameters. The first parameter is a function from a to a. The second parameter is a value of type a, and then we're simply getting back a result of type a. So it's a curried polymorphic function whose first parameter or whose first argument is a function. So again, the type makes very clear that it's a higher order function. You might be thinking, well, why does the function have to have type a to a and not a to b? Well, it's because we're applying it twice here. So we're applying f to x, and that will give us a result, and then we're applying the function again to that result to give the final result of the function. So in order to apply a function twice, if you kind of think about it and track through the types, it needs to have type a to a rather than a to b. So what could you actually do with the twice function? So a simple example of this is if you consider the increment function, which in Haskell you can define simply as +1 in round brackets. So +1 is a section that adds 1 to whatever parameter you give it. So for example, if you started up GHCI, you typed in this twice definition, and then you said what is twice of in brackets +1 and then 3, then it would apply the +1 function 2 times the 3 and you would get the result of 5 back. Okay, so very nice simple definition, very simple example here. So then you can ask yourself, well, why are higher order functions actually useful? So here's 3 reasons explained in the bullet points. So the first one is that common programming idioms or common programming patterns can often be encoded as functions within the language itself by using higher order functions. And we've just seen an example of this. Maybe you're writing a program and you find you're applying functions twice all of the time. Rather than doing that manually, that idiom or that pattern could be encoded as the higher order function twice. And the part that changes, the function f, becomes the parameter of the higher order function. If you take this idea of capturing programming idioms or programming patterns further, you end up with what's called domain-specific languages, or DSLs. So DSLs, or domain-specific languages, can often be defined as collections of higher order functions. And if you look at Haskell libraries, they are often defined in this manner. So for example, if you look at the way that Haskell deals with input-output, parsing, pretty printing, graphical user interfaces, sound, financial contracts, all different sorts of libraries are defined as domain-specific languages as collections of higher order functions. And the last one here is saying that algebraic properties of higher order functions can often be used to reason about programs. So what does this mean? So when you're at school, you learn algebraic properties of numbers, like x plus y is y plus x. That's the commutativity of addition. And those kind of algebraic properties are useful for reasoning about numbers. And it turns out that algebraic properties of higher order functions are also useful for reasoning about programs. So this is a programming course, it's not a reasoning course. I mean, if you're interested in kind of reasoning, I do an advanced functional programming course in second year. But we're going to come back to this a little bit later on, and I'll just give you a flavor of the kind of algebraic properties that you can use to reason about higher order functions. So we'll come back to this briefly later on today. So what I'd like to do now is give you 3 very common examples of higher order functions from the list library in Haskell. And the first 2 are very straightforward, and then the third one is a little bit more sophisticated, but as we'll see, it's also a lot more powerful. So the first function I want to think of here is called map, and it's a higher order library function that applies a function to every element of a list. So let's look at the blue box at the bottom first of all, which gives us an example. So I've started up GHCI and I'm mapping the increment function +1 across the list of the first 4 odd numbers, 1, 3, 5, and 7. And all it's going to do is exactly as it says at the top. It takes that increment function, applies it to each one of those numbers one at a time, and then you'll get back the first 4 even numbers, 2, 4, 6, 8. It's a very simple, very widely used function in the language. And if you look at its type, in the top blue box, this makes very clear, or absolutely clear, that it's a higher order function. So map takes a function from A to B as its first parameter, then it takes a list of A, and then it's going to simply apply that function all the way across the list, and it's going to give you back a list of B. So it's a curried function. It's taking 2 parameters one at a time. It's also a polymorphic function because we have the type variables here, and it's also a higher order function because its first parameter is a function from A to B. So there's quite a lot of things going on in the type there. So then you can think, how do you actually define the map function? So map has a very simple one-line definition using a list comprehension, which is something we covered in lecture 5. So the definition here simply says if you're mapping a function f across a list x's, all you're going to do is build the list of all values f applied to x, where x comes from the list x's. So it's if you're thinking kind of operationally, it's like a little loop. X is ranging over everything in the list, and then you're simply applying the function to each one of those things. So it's a very simple one-line definition by exploiting the power of list comprehensions. What we see in the second half of the slide here is an alternative recursive definition for the map function. And you might think, well, why should I ever prefer to define it recursively when I could define it in a one-liner using a list comprehension? Well, as it says on the slides here, if you were interested in doing reasoning about your programs, and then you define your program using recursion, then you could use the mathematician's tool of induction to do reasoning. And again, we're not going to be doing that kind of thing in this course, but I just want to also, for interest, just show you how you can define map using recursion. So there's 2 equations down the bottom. We have a base case, first of all, that says if you map a function across the empty list, well, there's nothing to do. There's no elements, so you simply get back the empty list. So that's the base case. And then the recursive case tells you what to do with a non-empty list. So we're saying if you map a function f across a non-empty list whose first value is x and whose remaining list of values is x's, then the right-hand side tells you what to do. So all we're going to do is simply apply the function f to x and then recursively map the function across the remaining list, and then we'll just put that first value f of x together with that mapped list using the colon operator. So a nice simple 2-line recursive definition. So the second function I want to tell you about is the higher order function called filter. And what it does is it gives you a way of throwing things away from a list or dually keeping things from a list. So the higher order library function filter selects every element from a list that satisfies a predicate. So what's a predicate? Well, it's just a fancy word for a property, and a property is just a fancy word for a function that returns true or false. So if you look down at the bottom, we have an example as usual. Here we are filtering the even numbers from the list 1 to 10. So even is a predicate or a property, and what that simply means is it's taking, in this case, an integer as an input and giving back true or false, depending on whether it's even or odd. And then this example does exactly what you expect. You filter the even numbers from the list 1 to 10, and actually you'll just get the 5 even numbers back: 2, 4, 6, 8, 10. And then again, we can look at the type at the top of the slide. Filter is a higher order function which takes a function as its first parameter, takes a thing to a boolean. It's a polymorphic function here. And then we're taking a list of A things, and finally we're getting back also a list of A things as well. So whereas map applies a function all the way across a list, filter is only going to select those things that satisfy a particular property. So it gives you a way of throwing things away. And again, there's two, or at least two, natural ways to define the filter function. There's also a very simple one-line definition using a list comprehension. We can simply say if you filter some property P over a list X's, then you do what it says on the right-hand side. And the right-hand side's got one generator and one guard. So we're forming the list of all values X such that X is drawn from the list X's and P holds true for X. So we've got a little loop which is ranging over X's, and we're considering each value X one at a time, and then we're only going to keep those values or if the property P is actually true. So again, nice one-line definition using a list comprehension, and we have one generator for the variable X, and then we have one guard which is filtering out things that satisfy the property P. So very, very straightforward. Alternatively, it can be defined using recursion as well. So there's a few more lines here. There's 4 lines here, or really 3 lines. I've had to squash it a bit to fit it on the slide. So the base case is again very, very simple and very trivial. If you filter a property P and the list happens to be empty, there's no values to consider, so you simply return the empty list. And then the interesting case, as usual, is the recursive case. This says if you filter a property P over a non-empty list whose first value is X and whose remaining list is X's, then you have a choice to make. So we've got 2 guards here, P of X and otherwise. So in the first case, if the property P holds or is true for the value X, then we're going to keep it. So on the right-hand side, we have X colon filter P X's. So that's simply saying if the property P is true of the first thing in the list, we keep it, and then we recursively filter everything in the remaining list. Otherwise, then that means that the property P was not satisfied. So for example, if P was even, then this would mean that the number was not even that we were looking at. So in the otherwise case, we don't mention X because it doesn't satisfy the property P, and we simply just continue by filtering the remainder of the list. So again, nice simple one-line definition at the top, and then if you preferred, for example, for the purposes of proof or just practicing your recursive programming, this is how filter can be defined. So the next function that we're going to look at is a bit more abstract than the previous two, but as we'll see, it's much more powerful, and it's called the foldr function. And as we'll see, foldr stands for folding to the right or fold right. And the observation, or the starting point for the foldr function, is a very simple one. So a number of functions on lists can be defined using the following simple pattern of recursion in the blue box. So here we're defining a function called f, which is going to process a list. And it's got 2 cases. The first case, the base case, simply says if you apply the function f to the empty list, then you get back some fixed value v, so some constant value v. And the recursive case says if you apply the function f to a non-empty list, where x is the first thing in the list and x's is everything else, then all you're going to do is you take the value x and then you recursively process the remainder or tail of the list by applying f to it. So you apply f to x's. So now you have two values. You've got the value x and the recursively processed tail, f of x's. And then you're going to combine those two values using some infix operator, which I've written here as the plus with a little circle around it. That just stands for any old generic infix operator. And you sometimes pronounce this as plusle. Okay, so just to kind of reiterate what's going on here, we're defining a simple function by recursion, and this is a very common pattern. The empty list goes to some fixed value v, and any non-empty list is processed by applying some infix operator, plusle, to the first thing in the list and the recursively processed tail. So a couple of points to note here. The first one is that this on its own is not a valid function definition because I don't know what v is and I don't know what plusle is. This is just a pattern. This is a simple pattern of recursion which you see all the time. And actually we've seen many examples of this already, and we've already seen the name of this pattern. It's sometimes called primitive recursion. So if a function is defined by primitive recursion, it's defined in this kind of pattern here. So we have seen a number of examples before of this. So here's three very simple examples. I think we've seen all of these before. So the first one is the summation function. So we're summing a list of numbers. We have a base case. If we sum the empty list, we get 0. If we sum a non-empty list, we get x plus the sum of the tail. And that precisely fits the pattern of primitive recursion, where in the base case, we're returning the constant value 0. And in the recursive case, the operator we're using to combine the results is simply addition. Okay, so this matches the pattern where v is 0 and the plusle operator is just normal infix addition. Exactly the same pattern occurs with the product function, except in this case, in the base case, we return 1. And in the recursive case, we're processing the first value and the recursively processed tail by applying the product or multiplication function. And then right down at the bottom, we have logical AND, which takes a list of logical values or booleans and only gives back true if they're all true. Again, it fits this simple pattern where in the base case, we're returning true, and in the recursive case, the operator, which we're combining things with, is the infix double ampersand operator, which simply takes logical AND of two logical values. So very simple pattern. Here we have the pattern. Here we have three examples of this in practice. So what the library function, or the higher order library function called foldr, which abbreviates fold right, what it does is it encapsulates or abstracts away from this pattern. And it simply takes the function plusle and the value v as arguments. So for example, here are very simple one-line definitions for how to define a bunch of functions which fit this basic pattern of recursion, which is captured by foldr. So if I wanted to define summation using foldr in the first line in the blue box, all I need to do is supply it what to do in the recursive case, that's the addition, and what to do in the base case, and that is 0. And the foldr operator, or the foldr higher order function, will take care of all the recursion for me. All I'm basically doing is saying, what's the operator in the recursive case? What is the value in the base case? And it deals with the recursion for me. So product, we can also have a very nice one-line definition. Product is simply folding, where in the recursive case you do a multiply, and in the base case you just return the value 1. And then at the bottom we have OR and for lists of logical values. And again, these have a simple one-line definition using the foldr operator, just by applying the appropriate operator and the appropriate base case value, either false or true. So then you can think, well, how does foldr itself actually get defined? Well, let's have a look at the definition in the blue box here, and we'll come back to the type in a second. So the first line of the definition says, if you're applying foldr with a function f, so that's going to be the operator which you apply in the recursive case, and then you have a value v, that's going to be what you return in the base case, and then in the first equation, we're saying if you apply this all to the empty list, then, well, that is the base case, so you simply return the value v. So in the recursive case, what it's saying is if you're folding and you have a function f and a value v and you have a non-empty list, well, what do you do? Well, when you look on the right-hand side, you see in the brackets, you're recursively folding the remainder of the list. So that's recursively processing the remainder of the list in the same way. So now you've got two values. You've got the first value in the list, x. You've got the recursively processed remainder of the list. That's the stuff in the brackets. And all you do is you apply the function f, which is the first parameter to the folder, to those two values. So this is capturing, in a nice simple two-line recursive definition, what it means to have that simple pattern of recursion. And again, if we look at the type, we can see it's a curried function. It's taking three inputs one at a time. It's also a polymorphic function because we have the variables a and b. And it's a higher order function because the first parameter is a function from a to b to b. So I'll leave you to kind of think about that type in a bit more detail yourselves. You could kind of try and cover up that type and try and work out why the first function is an a to b to b rather than something else like an a to b to c or an a to a to a. This is the most general type which the folder function could have. So it's a nice simple two-line recursive definition, but actually I like to think of folder non-recursively, and the way you can do this is as a little trick. You think of it as replacing each of the colons in the list by a given function, that's going to be the f, and you're replacing the empty list at the end by a given value, that's the value v. So I want to give you a couple of examples of this now, and then we'll think about what more kind of sophisticated things you could actually do with the folder function. So let's think about this idea of folder simply replacing the colon by some operator and the empty list by something else. What do I actually mean by this? So suppose we're trying to sum the list 1, 2, 3. So we could replace that by simply folding with the plus operator and 0, because we know that's how we could define summation. Summation is just folding, where in the recursive case you do an addition, in the base case you do a 0. So that's all that I've done in this first step. Then in order to make sense of this, what I'm going to do is expand out the list 1, 2, 3. So if you can remember when we talked about lists a few classes ago, when you have a list like 1, 2, 3 in square brackets, it's really built up in a more primitive way by starting with the empty list and then putting values on the front one at a time using the colon operator. So then you can think, well, what happens when you actually run this thing? Well, I like to think of folder non-recursively as simply taking the list, like 1, 2, 3, empty, and it's going to replace each of the colons by whatever operator you give it, or whatever function you give it, in this case the plus, and it's going to replace the empty list at the end by 0. So if we take that list, 1, 2, 3, with the empty list at the end, and we replace each of the three colons by a plus, and the empty list at the end by 0, then we get exactly what we expect. We get 1 plus 2 plus 3 plus 0. And I've kept the brackets in so I don't mess up. And then you could actually do the addition and you get 6. Okay, so this emphasizes the idea that folder is fundamentally building your recursive functions, but it's very useful to think of those functions non-recursively as just replacing the two constructors for lists, which are the colon and the empty list. You replace them by whatever you want. So in this case, we're replacing the colon by addition, and we're replacing the empty list by 0. So it gives you a different way of thinking about what summation is actually doing. So we can just have one more little example of this before we move on to some more sophisticated examples. Here's product of the list 1, 2, 3. Product we could define by folding. In the recursive case we multiply. In the base case we give back 1. Then we can expand the list, so we get 1, 2, 3, empty. And now we can think of this substitution or replacement process. All we're going to do is replace the three colons, in this case by multiply, and the empty list at the end by 1. So when we do that replacement, we get 1 times 2 times 3 times 1, and then finally we're going to get back the result 6. Okay, so what we've seen now is two simple examples of how we can think of folder non-recursively in terms of just replacing the two constructors for lists by whatever we like. So what we've seen now is how folder can be used to define a number of simple functions on lists in a one-line manner. But actually, folder gives you a lot more power than you might first expect. So the observation at the top of the slide here is even though folder encapsulates a very simple pattern of recursion, it can actually be used to define many more functions than might first be expected. So let me give you a few examples of these, and these get kind of increasingly more sophisticated. So here's our old friend, the length function, and it simply takes a list of things and tells you how many things is in the list. And it's got a simple two-line recursive definition. If you wanted to define it using recursion, the length of the empty list is 0, and the length of a non-empty list is 1 plus the length of the tail of the list, so x's. And notice here that the length doesn't depend on the first value in the list, so I've used a wildcard character, the underscore character, rather than matching on a non-empty list x colon x's. I don't actually care what's in the list or what the elements are, so I'm replacing the x variable here by an underscore. So this looks pretty much or pretty similar to the pattern of recursion that we have seen. So we have a base case that's simply returning the value 0. In the recursive case, we're doing an addition, but there's something a little bit different. So notice here we're not saying x plus the length of x's, we're saying 1 plus the length of x's. So it doesn't seem to quite match the pattern which is captured by folder. But actually the trick here, which lets us actually define this using folder, is that the operator, which we're using in the recursive case, the plusle, which we're supplying as an argument to the folder function, that can do whatever we want. So it could ignore its first argument and just do 1 plus whatever the second argument is. And that observation, that you can do whatever you want with the function, the plusle for the folder, and whatever you want in the base case, actually allows you to define more functions using folder than you might first expect. So let's see then how we could define length as a fold. So what does length do? Well, let's first of all expand out the list. So if we're taking the length of the list 1, 2, 3, we write it in the more primitive form so we can see actually what's going on under the hood. So it's 1 colon 2 colon 3 colon the empty list, all bracketed to the right. And then if we actually unwind the recursion for this function, what's actually happening is we're getting 1 plus 1 plus 1 plus 0. And now we can think, well, what's going on here in terms of substitution? Well, it's easy to see what's happening with the empty list. So the empty list at the end is simply being replaced by 0. That was the base case of the definition. And then what's happening to each colon? Well, what's happening to each colon is it's being replaced by the function which simply adds 1 to whichever its second argument is. So it's kind of replacing each colon by 1 plus. And that's what's captured in the brackets here. If we replace each of the colons by the function that takes 2 parameters, we don't care what the first one is. So we have an underscore, and then the second parameter is n. That will be the result of recursively computing the length. And then we return 1 plus n. That's the appropriate function to do in the recursive case. In the base case, we're just simply replacing the empty list by 0. So notice here we're using the lambda syntax to build an anonymous function. Lambda underscore n, arrow 1 plus n, is the anonymous function, the lambda expression, that takes 2 parameters, doesn't care what the first one is, and then gives you back 1 plus whatever the second thing is. Okay, so what this is telling us is if we put all this together, we can compute length by folding. So we call folder with the function lambda underscore n, arrow 1 plus n. It simply adds 1 to whatever its second parameter is, doesn't care what the first parameter is, and then we give 0 in the base case. Okay, so nice, simple one-line definition for the length function. And the trick here is that initially, if I go back to the definition, it doesn't quite seem to match the pattern of recursion, which is captured by folder, because we have 1 plus in the recursive case rather than x plus. But the trick is we're allowed to do whatever we want with the function, so we just pass in a little lambda function that does exactly what we want. So we can define length using folder. Let's have another example, which again, this is one we maybe need to think a little bit to see how does this fit the pattern of recursion which is captured by folding. So here's the reverse function, defined using recursion. The base case is easy. If you reverse an empty list, you get back an empty list. The recursive case says if you reverse a non-empty list, x is the first thing, x's is everything else, then on the right hand side you see what to do. So you simply reverse the tail of the list, and then you put the first thing, x, in a little list on its own, and then append that on the end. So you can think, well, does this match the pattern of recursion captured by full-dir? So the base case is easy, we're just getting the empty list back. That one's no problem. In the recursive case, something as funny is going on. We're not taking x combined with reverse of x's in that order. We're doing reverse of x's and then combining it with x put into a little list with an append. So things have kind of been flipped from the left to the right. On the left-hand side of the equation, we have x colon x's. And on the right-hand side, we're first of all processing x's, which is the second part of the list, and then we're processing the x afterwards. So we're kind of flipping the order of the arguments on the right-hand side. And then you can think, well, how can I actually define this using full-dir? And again, the trick is the operator which you combine, or which you use in the recursive case, that could do that flipping for us. Okay, so let's see how this works with a simple example. So here I'm reversing the list 1, 2, 3. Then if I write the list in internal form, that'll be 1 followed by 2, followed by 3, followed by empty. If I unwind all the recursion and kind of turn the handle with that, as we've seen how to do in the past, here's what I'll get. And I get, in the end, when I do all those appends, I'll get 3, 2, 1. And if you think what's actually going on here is each colon is being replaced by this particular lambda expression. So what we're doing in the recursive case is we're taking the first value in the list, which is x, the remaining recursively processed list, which is x's, and then all we're going to do is flip the order of those and put the x on the end. So we'll do x's plus plus, and then we'll have the singleton list x. And this is what will be happening in the recursive case. And the full-dir will take care of the recursion for us. And then in the base case, we're simply replacing the empty list by the empty list. So to sum up, what this is telling us is if we wanted to, we could define the reverse function by folding. So you fold with that lambda expression there, which we've just been thinking about, and then in the base case, you simply have the empty list. So I wouldn't argue that this is a particularly nice, easy to understand definition. It's really just a game here. We're thinking, how powerful is the full-dir operator? Can we do things with it which you might think at first sight that you're not able to do? And the answer, as we're seeing here, is yes. So just to wrap this particular example up, I want to kind of note that also the append function, plus plus, this has got a very, very concise definition using full-dir. So we've seen previously, if you look back to lecture 6, you can see how to define plus plus or append using recursion. It actually satisfies or is an instance of the general pattern captured by full-dir. So here's the definition, and it's very, very concise. It says if you want to append any old list y's to the end of another list, all you do is fold, and then you have colon and y's as the two arguments. So what's actually going on here? Well, this is extremely intuitive. If you imagine you've got some list x's and you want to append y's onto the end of it, then how would you actually do that? Well, all you do is you walk down the first list and you copy it. Okay, so you copy the entire first list. So that means you replace all the colons in the first list by colons. That's how you could copy the list. And then once you reach the empty list at the end of the first list, you replace that empty list by the second list, y's. So that's all that's going on here with this definition. It's just expressing very concisely, if you want to stick one list y's onto the end of another list, all you're going to do is in the first list, replace each of the colons by colons, and then when you reach the end of that first list, you just copy in the whole of the second list y's. Okay, so again, these two definitions here, you might need to kind of pause the video, kind of stare at these for a little bit, maybe try typing them in and running them for yourself, kind of turning the handle and seeing what's happening. But it's kind of the point of these examples is to show you that this full-dir operator is a very simple pattern of recursion, but you can actually do much more with it than you might actually think. So just to wrap up the full-dir story, you might be thinking at this point, well, is this just an exercise for torturing people who are learning Haskell? And actually there's three good reasons why full-dir is actually useful. So the first one is that sometimes it's a very nice, simple way to define things. So for example, if I was defining sum, product, and, or, these had very simple, nice one-line definitions using folder. I think that's a very simple and elegant way to define them. So some recursive functions are simpler to define using folder. Something which is very interesting is that properties of functions defined using folder can be proved using algebraic properties of folder. And these have some funny names. They're called things like fusion, which is the idea of kind of combining programs in sequence and trying to optimize a sequence of programs into a single program. And there's other rules like the so-called banana split rule. The folder operator is sometimes written using kind of funny banana brackets, if you look in the literature. And there's a so-called banana split rule, which is to do with kind of transforming programs written using folder. So the second idea here is if you define your programs using folder, you can reason about them using algebraic properties of folder, such as fusion and the banana split rule. And again, you might think, well, I don't care about stuff like that. I'm just a programmer. I want to learn how to write nice, clear, efficient code. But actually, this is advanced program optimizations can be simpler if folder is used in place of explicit recursion. And this is actually one of the key tricks which is used internally to the Glasgow Haskell compiler. So if you think about the list library, it's got things like map and filter and length and so on. Internally to the Haskell system, these are actually defined using folder. And then the Glasgow Haskell compiler uses algebraic properties, in particular fusion properties of folder, to try and optimize your programs to make them run much faster. Okay, so even though you might not care about things like fusion and banana split, these are kind of more sophisticated topics which we'll cover in the advanced course in the second year. Even if you don't care about them, the compiler cares about them because it's using these kind of things to optimize your program for you. Okay, so that's all we're going to really think about in terms of folder. Captures this more kind of sophisticated pattern of recursion, or a simple pattern of recursion, and it's actually more general than you might think. So the last thing I want to do today is show you a few other examples of library functions which turn out to be higher order functions. And we're going to zip through about 4 or 5 of these. So the first one I want to show you is what's called function composition, and it's a very simple idea. It's just applying two functions, one after the other. So we can see an example of this down at the bottom of the slide. Here I'm defining the odd function, which takes an integer as its input and gives you back a boolean as an output. And what does it mean to be an odd number? Well, one way of defining it is it's not even. So a number is odd if it's not even. So we can express this very nicely as the composition of the not function and the even function. So the dot, or the full stop, that's how you write function composition in Haskell. So the equation at the bottom says I'm defining the odd function simply to be the composition of the not function after the even function. So odd is simply not composed with even. So how is function composition actually defined? Well, we see that in the top blue box, so let's have a look at the definition first. So the definition says f composed with g, so f.g equals, and then we have the actual definition. So what does it mean to compose the function f and the function g? Well, all we're going to do on the right hand side is we're building a function. So we're using the lambda notation here. So we're saying we take an input called x and then we simply cascade it through the two functions, one after the other. So first of all, we apply the function g to x. That will give us a result, and then we apply the f to that, and that will give us the final result. So if we looked at the example down below, we say odd is not composed with even, then the function f would be not, the function g would be even, and on the right hand side we'd be taking a number x as an input, we would be applying the function even to it, so that would give back true if it's even and false otherwise, and then we would be taking that result and applying not to it, which would flip it. Okay, so function composition, really simple idea of just cascading or applying one function after another. And then you can look at the type, and the type here is interesting because this is an example of a higher order function which both takes functions as an input and gives back function as a result. So it takes a function from b to c, then a function from a to b, and finally gives you back a function from a to c. And you might think, well, where are the A, B's and C's in that particular order? And you can check this for yourself. If you kind of behave as the type inference system of the Haskell compiler and kind of cover up the type and think, well, what's the type of F? What's the type of G? What types do they need to have so that I can apply the function G and then feed its result into F? And if you kind of track through all the details for yourself, you'll find that this is the appropriate type for function composition. So what I want to show you kind of now quite quickly actually is just 4 other useful library functions for processing lists. So the first one here down the bottom, all, it takes a property such as even, and then it's going to give you back true if all the numbers in that particular list have the property of being even. So in this case I've got 2, 4, 6, 8 and 10. These are all even numbers, so we're going to get back true. So in general, all is a higher order function. It takes a property and it takes a list and it only gives back true if every element in the list satisfies that property. Okay, so if we look at the type, all takes a property or a predicate from A to bool, takes a list of A and it gives back a bool. And the definition is very simple. All P of X's is simply going to be in the list comprehension, we check is the property P satisfied for every value in the list. So that list comprehension will give us back a list of trues and falses, matching up on each element in the list. And then we only want to give back true if all of the things in that list are true, so we can just AND all of that list together. Okay, so a nice one-line definition for all. Any does the opposite. If you look at the definition, it's the same except we write or rather than and the idea is that any decides if at least one element of a list satisfies a predicate. So whether any element in a list satisfies a property or a predicate. So down at the bottom, here's a nice example of this. I'm saying, are there any space characters in that particular string? And yes, there's one in the middle, so we get back true. Okay, so if you're doing some simple parsing or something like that and you wanted to say, is there any space characters in a particular string, you could just say any equals space and then the string, and then that will check, is there any spaces in the string for you. So again, nice simple, very widely used higher order function. So the last 2 functions I want to show you are called take while and drop while. And what take while does is that if you look at the example down the bottom, it takes a property and it's going to consume values from a list while that property remains true. And as soon as it finds a single value which doesn't satisfy the property, then it's going to stop. So in this case, we're wanting to take while does not equal a character, so the / equal is not equal to, so we want to take while we don't have a character, we don't have a space character rather, and then we take the string and it's going to consume characters until we find a single space and then it will stop. Okay, so again, this is you could use this to do some simple parsing. If you wanted to split a string where you find the first space, you say take while doesn't equal space and then the string and it will split it. So in this case, you just get the ABC and it throws everything else away. And I won't go through the definition this time. It's a simple higher order function. Here I've defined it using recursion, and you could have a look at the definition for yourself. It's just a simple kind of 3 or 4 line recursive definition. Drop while does the opposite. If we look at the example at the bottom, if you wanted to do some simple parsing and you wanted to get rid of any leading spaces in a string, you could say drop while equals space and then the string, and this will, while that property is true, it will keep throwing the space characters away until it finds a non-space, and then it will give you everything else back. So again, it does exactly what it says on the tin. Drop while takes a property and it removes elements. It removes elements while that property is true, and then it gives you back everything else. So that kind of wraps things up for today. We have a few exercises, but I'm actually going to swap over to my iPad to go through 1 or 2 of these. So the first exercise is a simple question. What are higher order functions that return functions as results better known as? And this is one of these exercises where if you see the answer, it's very easy. And if you don't see it, you think, well, actually, I've got no idea what the answer is here. So the answer is actually very easy. It's curried functions. So let me give you an example that explains why higher order functions that return functions as results are just curried functions. So let's have a look at a library function. Let's have a look at the take function, and it's a curried function. It takes an integer as its first parameter, and then it takes a list of things of any old type A, and then it's going to give you back a list of things of the same type. And again, it's a curried function. It's taking an integer, and then separately it's taking a list, and then finally it's giving you back a list. So it's a curried function, and one of the things we learned about curried functions is when you have repeated uses of the arrow, they bracket towards the right. So when I write this type here, what I really mean, if I was to put brackets in, and let me do this in red, the brackets go here. So what you see now is that this curried function is actually a higher order function which is returning a function as a result. And you see that precisely in the type. We're taking an integer as an input, and then we're getting back a function which is going to take the second input. And that function takes the list of things and then finally gives you back the list here. So this kind of simple example shows you that higher order functions that return functions as results, these are just curried functions. So a nice, simple, easy answer to this exercise. So let's move on to the second exercise. So this is a nice one, and what I've given you here is a simple list comprehension. It's got one generator, which is x ranging over x's, one guard, and then we're applying a function to everything that remains. And the name of the game here is you have to redefine or re-express this list comprehension using two of the higher order functions which we learned about today, which are map and filter. So this is a nice easy exercise, but there's an easy way to get it wrong. So I'll show you how to do it correctly first of all. We just simply write down, this is a map, f after the result of filtering p from x's. So why is this correct? Well, if you look at the list comprehension, what we're doing is we're ranging over each value in the list, only keeping those that satisfy the property p, and then for each of those, we're applying the function f to it. And that's exactly what I've expressed down below. What I'm doing here is, first of all, only keeping the values that satisfy the property p, and then for each of those, I'm going to apply the function f. So this is how to do it correctly. Let me just show you one way that would be easy to do it incorrectly, and this is a very common mistake if I ask something like this in the exam. Here is how to do it incorrectly for this particular example. So I could get the map and the filters the wrong way around. So this one would be applying the function f to everything in the list x's first, and then afterwards it would be only keeping those that satisfy the property p. And that's not what's going on with this list comprehension. With the list comprehension, we're doing a filtering first, and then secondly, we're applying the function f. Okay, so if you did this in the exam, this one, the first one, would be correct. You get full marks. This one would not be correct, so you wouldn't get any points. So that's it for today. I will see you again next time around.